Let's study ESA2H, controlling errors with algebraic computation. The main text is available at K-pop Digital Library. And if you visit kpop.org and you find a table of contents, you can click Escape from Scientific Absurdity, Series A, and you arrive at A2, controlling errors with algebraic computation. This file is a helper, that is H, indicated by H, and the main text is given here, and the corresponding YouTube file is next. So you can click this to find the main text, and please be prepared to understand the basic strategy to carry out systematic error analysis using very simple formula that is square of x plus y is x squared plus 2xy plus y squared. Using this very simple formula that we learned in the middle school can be used to estimate the approximate value for the square root of 2 with an arbitrary accuracy if you require. Okay. And let's return to the K-pop Digital Library. If you click this, you'll find the explanation, my lecture explaining what's going on in this lecture. So, I do not want to give a lecture redundant. Instead, I prepared a little bit different version, or more practical version, to prepare for your beta exam. So this is H. Let's see, the pendulum clock. So now we seldom use a pendulum clock, but when I was young, it was very popular. It began with Galileo's experiment, and actually he noticed the isochronism of the pendulum. Independently, the period is fixed once the length of a pendulum, sure, its mass is also fixed. The length of the pendulum is fixed, then it is virtually independent of the amplitude. What is? That is the period of a pendulum. In 1637, Galileo Galilei designed a pendulum clock that was not completed. However, later, Christian Huygens he developed further based on the idea of Galileo Galilei, and he invented this pendulum clock. Wait and see. Okay, if you visit our K-pop neighbor cafe, there's a place in here, the board with the symbolic algebraic computation. You will find this copy of this related version. So Christian Huygens patents the first pendulum clock. You can click this to find further details from the APS.org, that is American Physical Society. All right, so Christian Huygens found this formula. Later in this semester, we'll find how this formula derives, but let us just forget about the derivation of this formula. Instead, why don't we make use of this to determine the period when the length L of the pendulum varies from an initial value. Here, G is the acceleration. What kind of acceleration? Gravitational acceleration. Most of you might know the gravitational acceleration is a 9.8 meter per second squared. Who patented pendulum clock first? You know this. I told you just before. 2. Period of pendulum. A pendulum, the mass, it is also called a bob. The turning point is the position at which a pendulum bob stops. The pendulum is like a swing. We have two stopping points. So before this bob reaches this point, it was moving to the left, and then at this point, it stops. And then after that, it returns to the bottom. So direction of motion changes at these 2 points. Because of the change in the direction, we call these points turning points. Turning points. So turning points. What is the period? The period is the time elapsed to make a complete cycle. So, go back and forth. So this is the period. So the time elapsed from the motion from a turning point to another is just only 1/2 of the period. Something like that. Simple harmonic oscillator. A simple harmonic oscillator is nothing but a mass spring system. Finally, we will eventually identify the motion of this pendulum is identical to that of the simple harmonic oscillator as long as the amplitude, this is the amplitude, as long as the amplitude is very small. Anyway, before we study further detail about the pendulum, we can consider a very, very simple system, a spring mass system. And there's a mass M and spring with a spring constant K. We call it a simple harmonic oscillator. The mass accepts the external force exerted by this spring that is proportional to the displacement from the equilibrium position, 0, equilibrium position, and if it moves, for example, to there, from this point, this is called the displacement x from the equilibrium point. Then, the force applied by the spring is proportional to the spring constant and proportional to the displacement. In addition to that, it has a negative sign. This force is directed opposite to the displacement from the equilibrium position. Okay, this is the system called the simple harmonic oscillator. Later, we will learn that solution of this motion, this equation of motion for a simple harmonic oscillator, is a linear combination of sinusoidal function. Sinusoidal function is a sine, either sine or cosine or sine with the phase shift. Delta is called phase shift. Okay? So as long as this sine and cosines are concerned, and any kind of sinusoidal function shifted with the phase shift delta, as long as the period, the shape is a sine of x, cosine of x, and a sine of x plus something, there is no additional factor in front of x. So in that case, all these kinds of sinusoidal function are to be added to make a result a single sinusoidal function. All right, so we call it a linear combination of two sinusoidal functions with the same period is another sinusoidal function with a single sinusoidal function with the same period. Let's see what the period is. A function is a periodic. A function is a periodic if I substitute some period, the value of the function is the same, invariant. So that means it has a translational symmetry. This translational symmetry of sign, this sign, and if I shift this one a little bit, they are different. But if we go further to make it overlap with the previous one, that means if I shift this point to there, in that case, this function is original function is reproduced. This kind of translational invariance of a function is called periodicity. It is periodic with the period. For example, we have a sine and cosine whose period, so peak to peak distance is the period, and this period for sinusoidal function with sine of x is 2 pi, the 360 degrees. Okay, let's see. If I add this argument by 2 pi, the result is the same. So I can do the same job repeatedly and by n times, and the result is sine of x plus 2n pi, where n is an arbitrary integer. Then it is identical to the sine of x. So it is a periodic with the period 2 pi. What about the case x has additional factor a that is not equal to 0? The sine of ax plus 2 pi should be the same as sine of ax. Okay, so the period of this sine function is 2 pi, but what about the case of sine of ax? This is the case. A times this shifted amount should be 2 pi. Okay, why? Ax plus the 2n pi. This 2n pi is the same for x and for ax together. However, if I factor this a out, it is x plus 2n pi over a. So, what happens? While the period for a previous case was 2 pi, the period for this x variable, the sine ax plus something, or sine ax, it will return to the same value if I shift this argument by 2 pi, but the period multiplied by period varies for the variable x. So if I shift x by t, then because of this factor of a times t should be equal to the period of original sine function. As a result, a period of this sine of ax should be 2 pi over a. In this manner, we can determine the period or frequency of this sinusoidal function depending on time. Okay, frequency. Period of this function is, as far as we know, because this factor a is divided, period t of this sine of omega t is 2 pi over omega. I have replaced a with the omega. I can exchange these two to find omega is equal to 2 pi over capital T, that is a period. So if I factor this 2 pi out, then we obtain 1 over T, that is called frequency. So we have found these special characters. They are Greek characters. So it's better to memorize useful characters. You might know already about the alpha and beta. We have gamma, this capital gamma and lowercase gamma, delta, capital delta and lowercase delta, epsilon, zeta, eta, theta, iota, kappa, lambda, capital lambda and lowercase lambda, mu, nu, xi, pi, rho, sigma, tau, epsilon, phi, chi, psi, omega. Okay? Alpha is the beginning letter and omega is the last letter. Next we consider two square roots, x and x prime, whose argument is a little bit shifted by epsilon. That epsilon has a very tiny number in comparison with the original a. And for simplicity, we just consider the positive a. I'd like to make use of the previous result for the square root of a, and I'd like to find the shift from the original value if this change in epsilon is tiny, using power series expansion. We assume that we can make a series expansion because epsilon is small. Epsilon square is much smaller than epsilon, and it is much greater than epsilon cube and so on. Using this method, we can make a guess that x prime is a linear combination of epsilon's powers. The leading order, when epsilon vanishes, it is returned to the original value, and then we make a correction in linear term in epsilon, and then a little bit smaller, and so on. So we assume this power series expansion reproduces the full expression. But this is practically useful. We don't have to compute this one anytime. So, because this square root is a solution of a quadratic equation, so we can square this to find the square of this square root is a plus epsilon. So x prime squared is a plus epsilon. And then we square the right-hand side, and we know how to expand this. That is a squared to ab plus a b squared, and so on. What happens to the case if I have three terms, 3 squared and 2ab, bc, and ca? So in this manner, I can expand the right-hand side. However, what we are interested in is leading contributions in powers of epsilon. So for example, if I have squared this, I have gamma squared epsilon to the 4th power. But for simplicity, we just keep the leading contribution of epsilon to the 0th power and first order and second order. We are satisfied with the leading 3 terms. So this one, if I expand, the leading contribution is alpha squared, and next one is a product of this multiplied by 2. So 2 alpha beta epsilon. And next term will be square of this, that is beta squared epsilon squared. And then product of this will also give the squared contribution. However, it is a crossing term, so 2 times alpha times gamma appears. Comparing both sides, what sides? This one, left-hand side, has only the order epsilon and no more. That means this alpha squared must be the same as A, and order epsilon term, we have this factor should be 1, and then after that, every factor must cancel exactly. So it should be 0 epsilon squared, 0 epsilon cubed, and so on. Using these conditions, we can find the simple equations, and it is straightforward to find out the solution for alpha, beta, and gamma. And the final result is shown in here. And I can substitute these values to the original expansion formula. So I find it is expressed in terms of this. Okay? You can do it yourself. If you are not good at algebra, why don't you make use of reduced program that I have provided, so you can freely download the file and run the programs. Examples of the programs are already given in our Neighbor Cafe. Okay. For example, this is K-pop Neighbor Cafe, and if you click symbolic algebraic program in here, lectures, you might have noticed that there is a title with parentheses that has indication ESA2H. This one is related to the material that appears in the ESA2H. From next class on, I will indicate it is ESA3H, something like that. So this will be very useful to solve a bit of problems from ESA2 on. Okay, so why don't you click each of them and read it through and find out how the reduce operates and how this is how to make use of reduce to compute the tedious calculations. So please look at these information. Okay? That's it for today. Thank you.